This is Jack Jackson. In this video, we're going to start our playlist, actually the first of 3 playlists where we talk about quadrilaterals. Now, in our earlier weeks, in the earlier playlists, in my geometry section, we investigated the concept of length, line segments, angles, angle measure, and then we spent a few weeks investigating triangles, particularly focusing on triangle congruence. We found that hyperbolic, spherical, and Euclidean geometries all satisfied the side angle side SAS postulate, and also the angle side angle ASA and SSS side 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 triangle congruence theorems. We've also informally explored the idea of the sum of the measures of the interior angles of a triangle, and we've informally investigated the number of lines parallel to a given line through a given point. We found that hyperbolic, spherical, and Euclidean geometries behave differently in regard to these last 2 concepts, and we'll study these last 2 questions formally more in Chapter 8 below, or the next playlist. In this section, we'll begin a few weeks of focusing on quadrilaterals, and I consider the study of triangles and quadrilaterals to be right at the heart of any good high school or college course in geometry. I'm going to try to set up some of these videos so that they're going to be applicable to a high school geometry course, and of course also for my college geometry course, which is my primary audience. So I'm assuming that you're probably already familiar with the term quadrilateral from as far back as early elementary school. So how would we define the term quadrilateral? So what I'd like you to do now is see if you could just go ahead and pause the video and write down a definition of a quadrilateral. And when you think you've got a good definition, come back to the video and let's check it out. Press pause now. Well, let's think about this a minute. Let's first of all recall the definition of a triangle. We said given any 3 distinct non-collinear points A, B, and C, no 2 of which are antipodal, we define a triangle with these vertices as triangle ABC is defined to be the union of line segment AB with line segment BC, union with line segment CA. Now, this part about no 2 of which are antipodal, that really only applies to spherical geometry. So if you're only studying Euclidean geometry like in a high school course, you could strike that part and don't worry about it. But this other part is important. These points need to be distinct and need to be non-collinear. Okay, what problems? We found that there were certain problems if you didn't specify these things. For example, if the 3 points are not necessarily distinct, this could degenerate to a line segment or even a point instead of being a triangle. And if they're not collinear, then it would degenerate to a line segment or possibly a point if they're not distinct as well. The non-antipodal part is needed because we want these things to be actually line segments, and they're not line segments in spherical geometry. So here's the question. If you look back at your definition, did it take care of those problems and so forth? So what if we just, what problems could we have if we simply define a quadrilateral ABCD as a union of line segments AB, BC, CD, and DA? Were any of these issues with our study of triangles, and how should we define quadrilateral ABCD to avoid these issues? And are there other issues that show up with defining quadrilaterals that don't show up with triangles that we need to be careful about? Okay, so let's think about that a minute. Problem number 1. If the points include an antipodal pair, now this is only something for spherical geometry and non-Euclidean geometry. Recall that an antipodal pair is like the North Pole and the South Pole, this red thing here, ends at both of those poles. If you have an antipodal pair, then one of these things is not really a line segment. It's actually a ray going from A to A prime there. And so this shape, even though it's kind of like a quadrilateral, doesn't really quadrilateral in the sense that we don't have these line segments. So we don't even have line segments there all the time when we have some antipodal points. So we want to avoid that situation. So we're going to make sure we keep the non-antipodal as part of our definition. Also, a problem that came up with triangles was if the points are not distinct, then it could degenerate to a single point or a line segment or a triangle. And that problem exists in defining triangles. Also, a problem that we had, same problem we have with triangles, is if the three or more of the points are collinear, then the figure degenerates to a triangle or a line segment or another figure. It might not be simple or closed. And this was a potential problem with triangles if the points were collinear. Okay. And we have to be, even there, we have to be a little careful about doing this in quadrilateral. So we dealt with these problems fairly easily in the case of defining a triangle by just making sure the vertices were distinct, non-collinear set of points, not containing an antipodal pair. We've seen that we'll need to make these same restrictions when dealing with quadrilaterals. However, for quadrilaterals, it's not enough just to have the set of four vertices be non-collinear. We also need the set of any three of them to be non-collinear. For example, this triangle right here has A, B, and C collinear, but A, B, C, D is not collinear. And we don't want that to be a quadrilateral. So what if we have a definition for a quadrilateral that's like this? Given four distinct points A, B, C, D, no two of which are antipodal, and no three of which are collinear, let the figure be the union of A, B, B, C, C, D, and D, A. Let the figure, let me say specifically, let quadrilateral A, B, C, D be the union. So is this a good definition? Are there any further problems that could occur here that we did not have to worry about when we're defining a similar definition for triangles? Well, it turns out there's still a few problems that we have to avoid. Can you figure out what they are? Think about it for a minute. Press pause and come back. Well, here's a problem that comes up here. It's possible the figure could be non-simple. That is, as we trace around it, we meet the same point more than once, in addition to starting and stopping at the same point. In other words, two opposite sides could intersect. Now, we did not need to worry about this with triangles because it just didn't ever happen. But avoiding this case is particularly difficult, if not impossible, when you try to construct a general quadrilateral in GeoGebra or Geometry Sketchpad. But we really don't want figures like these to be quadrilaterals. So this yellow point here is a point that is on these two sides, but it's not a vertex. That's something we really want to eliminate. So we got to figure out a way to eliminate that. And there's another problem. The four vertices could be non-coplanar. Again, we did not need to worry about this with triangles because, and recall that any set of 3 points is coplanar, making the entire triangle coplanar. So the triangle was a figure that set in one plane. Well, we really want this same feature for quadrilaterals, but it's possible, for example, this definition that we have up here, incorrect definition, would allow not only this situation here, but it would also allow this situation here. Now think of this as a 3D figure. You've got a point here going along this edge of a box to another vertex, but then the fourth vertex is the opposite corner way up here. So now notice that there is no plane that contains all four. Of course, there are planes that contain any three of them, but not all four of those vertices. Now, you might find some geometry books that have definitions that allow one or more of these problems above to exist in their definition of a quadrilateral, but most geometers would like a definition that eliminates all of these problems above. So see if you can write a good definition out for a quadrilateral that eliminates all these potential problems. See if you can do it yourself. Press pause now. Okay, here you go. Here's a definition that does it. This could be a possible acceptable definition. Given four distinct coplanar points, A, B, C, D, no two of which are antipodal, and no three of which are collinear, Quadrilateral ABCD, written quad ABCD, is defined to be the union of line segment AB, line segment BC, line segment CD, and line segment DA if and only if no two of those four line segments intersects in points that are not in the set of vertices ABCD. That is an acceptable definition, and certainly we could go with that. However, we have even a few further problems to consider that we might want to eliminate when we can define things like a pentagon, hexagon, or a polygon in general. So it's really time to break down and go ahead and define what's meant by a polygon. To do this, we'll start by defining a more general class of geometric figures called curves. Now, we're going to informally to demonstrate or introduce what's meant by a curve. And so informally, we could do this with a bunch of elementary school students or junior high students. Informally, a curve is a set of points that can be traced by the end of a pencil without stopping the drawing. There are no breaks of any kind in the curve. It might be straight, like a ray, or a line segment, or it might be non-straight, like a circle, or a square, or triangle. It may have a finite length, like the line segment, or it may go on forever, like a line. It may cross over itself, like the numeral 8. It might begin and end at the same point, like a square. Or it might not. However, it needs to be one connected piece. And when introducing this concept to middle level students and secondary mathematics students, this formal description is sufficient. We can use a physical object like a piece of string to model a curve. That string could be laid on the table to represent a curve in a plane, or it may be moved out through 3 dimensions in space to represent a 3D space curve. Now, if you're in high school and you want to skip ahead of this next little piece, that's fine. So if students are not ready for the following formal definition, can skip ahead and it doesn't really lose too much. However, if you've had some calculus, you should have encountered the formal definitions of the limit of a function and a continuous function. If you're in my college geometry class, you've had at least a semester or two of calculus. We will use the formal definition of continuity, very similar to the definition you saw in calculus, and we'll see again in real analysis if you haven't taken that class yet, to formalize this concept. We also make use of parametric equation for a curve like you may have seen in Calculus 2 or Calculus 3. We talk about a curve being a continuous set of points. So here are the definitions. A curve, meaning a continuous curve, is a geometric figure C such that there exists a continuous surjective function f mapping I, an interval of the real numbers, onto C, the curve, okay, real numbers to points, right, called a parameterization of the curve, where I is an interval of real numbers or the entire set of real numbers, and C is a subset of the points in the geometry, in other words, a geometric figure. Okay, so what about continuity? What does that mean? Well, recall that a function is continuous at a real number a if and only if the limit as x approaches a of f of x equals f of a. A function is a continuous function if and only if the domain is an interval and it's continuous at every point in that domain. So going back to the definition of a limit, we further clarify this definition as the following. Let G be the set of points in the geometry, and we have a distance metric D mapping G cross G, ordered pairs in G, onto the interval 0 to infinity, including 0. That's the distance metric for the geometry. This could be onto or into in the case of spherical geometry, that interval. And F is going to be a surjective function from I to C, a parameterization of that curve, parametric equation for that curve. For any a in the interval I, and for any epsilon greater than 0, there exists a delta greater than 0, such that if x is an element of I, with the absolute value of x minus a less than delta, then the distance, using our distance metric from the geometry, from f of x to f of a is less than epsilon. In other words, if x is any real number of the domain sufficiently close to a chosen real number, measured by this absolute value of the difference in the domain, in other words, within d, delta, as measured by the absolute value of the differences in the real numbers, then the image points f of x and f of a, which are in our geometry, points in the geometry, are sufficiently close to each other within epsilon, as measured by the distance metric of this geometry. And this says that no matter what epsilon you pick, you can pick a corresponding delta. Under these conditions, I is a curve. And notice this is really just equivalent to how you define a continuous parametric curve in Calculus 2 and Calculus 3, but using the Euclidean distance metric. Now, I hope you've seen some of this idea of a delta epsilon definition of a limit in your Calculus 1 or 2 classes or Calculus 3. If not, you'll definitely see it in real analysis class. So this part of the course is a very much of an analysis kind of a feel to it. Okay, so once we have defined a curve, we can define several subclasses of curve and some related terminology. Once again, okay, if that part went over your head with that, just remember we can go back to the elementary school definition of the curve. It's basically something we can draw without picking our pencil up. It's one connected piece. So continuous basically means connected. Okay, so here's some definitions. A curve is a plane curve if and only if all of its points are coplanar. The whole thing exists in a single plane. A curve is a polygonal curve if and only if it is a union of line segments. So draw some line segments there, connected line segments. Informally, a curve is simple if and only if it does not cross itself. Although we do allow it to begin and end at the same point if we want, it would still be simple. Or it doesn't have to end at beginning at the same point. But otherwise, it doesn't cross itself. Now, if you think of that in terms of a parameterization, formally a curve with a parameterization f from I to c is a simple curve if and only if f of x equals f of y, the 2 points are the same, implies that x equals y for every x and y in the interval, with the possible exception that if the interval goes from a to b, then f of a equals f of b is allowed. So in other words, you can't get to the same place twice, except that you can begin and end at the same place. So the curve does not cross itself, basically. Informally, a curve is a closed curve if and only if it begins and ends at the same point. Formally, a curve with parameterization f, mapping an interval a to b, well, closed interval a to b, onto our curve C is a closed curve if and only if f of a equals f of b. It begins and ends at the same place. So the parameterization for a simple non-closed curve is a continuous bijection. A simple closed plane curve is also known as a closed plane figure. A region of space is connected if and only if given any 2 points in the region, there exists a continuous curve entirely contained in the region that begins at one point and ends at the other point. So a region is connected if you can start at one point and draw a continuous path, a path without picking your pencil up to get to the other point. Okay, that includes, of course, a region and a plane. The interior of a closed plane figure is defined to be the connected region bounded by the curve that is contained in the interior of a circle. So in other words, if you've got a closed plane figure, you should be able to draw a circle big enough so that the interior of the circle completely contains the interior of the closed plane figure. The exterior of this closed plane figure is the other connected region bounded by the curve. So notice that a closed plane figure partitions the plane into three pairwise disjoint sets, non-overlapping sets. The closed plane figure itself, the interior of the closed plane figure, and the exterior closed plane figure. An example of a closed plane figure, for example, would be a circle or a triangle, right? So you got the figure itself, and then you got the interior, which is bounded in area, and the exterior. A geometric figure is a polygon if and only if it's both a closed plane figure and a polygonal curve. Notice that we can view a polygon as a closed plane figure that's a union of coplanar line segments that only intersect each other at endpoints. But that's not enough uh, to be an actual definition. All right, now let's look at some definitions. A simple closed polygonal curve is a polygon. The line segments comprising the polygon are called the sides of the polygon. The endpoints of the sides are called the vertices of the polygon. Two vertices that are on the same side of a polygon are called consecutive vertices. Two sides are adjacent sides if and only if they share a vertex as an endpoint. The sum of the lengths of all the sides of a polygon is the perimeter of the polygon. The interior angles of a polygon, or sometimes just the angles of a polygon for short, are the angles that share a vertex with the polygon and contain a pair of adjacent sides. Two interior angles are consecutive angles if they are at consecutive vertices. Notice these are not adjacent angles. We have a definition of adjacent angles earlier that would not apply here. A diagonal of a polygon is a line segment which is not a side and whose endpoints are vertices of the polygon. Notice that lines, rays, line segments, and circles are all plane curves. A circle is a closed plane figure. Triangles and quadrilaterals are polygons. Note that some geometries have more lax definitions of polygons, which possibly include non-simple and or non-plane curves. If we eliminate the requirement of being simple, but keep the points coplanar, I would refer to this object as a polygonal closed plane curve. If we eliminate the requirement of being a plane curve but keep simplicity, then we have a simple closed polygonal curve. If we eliminate both the requirement of being coplanar and simple, then we have a closed polygonal curve. Notice that because we have already defined all these adjectives in our current context, all these terms have already been defined. Notice that all these types of curves are defined in Euclidean, hyperbolic, taxicab, and spherical geometries. General curves, as well as curves that are closed, non-closed, simple, non-simple, are basically identical in all four of the geometries as long as the points stay in the appropriate spaces. When it comes to plane curves, the interpretation of the plane is absolutely identical in Euclidean and taxicab geometries, so a Euclidean plane curve is identical to a taxicab plane curve. Similarly, a hyperbolic plane curve is a Euclidean plane curve, and a Euclidean plane curve in the upper half plane is a hyperbolic plane curve. Of course, spherical plane curves are not in Euclidean plane, but they are Euclidean 3D space curves. Euclidean and taxicab polygonal curves, including polygons, are identical, even though the lengths of the sides are measured differently in the two geometries. However, line segments look very different in Euclidean, spherical, and hyperbolic geometries, so polygonal curves, including polygons, will look very different in these three geometries. So the next thing is be sure that you can create curves of each of the following types above in Euclidean, hyperbolic, taxicab, and spherical geometries, and also be sure that you can determine if a geometric figure is or is not each of the types of curves above in all four geometries. So let's just look at a few things here as we might go through here. Let's see. So if we have something like a circle, set of points here, that is a closed plane figure. It is a curve. It starts and stops at the same point. Line segments are going to be a curve. That one's a non-closed, it is a simple polygonal curve. Here's an example the way I have it there, of a polygonal curve that's not simple, or that is simple. Here's one that's not simple, polygonal curve, but not closed. Now, if I close it up, it becomes a triangle. If I take it like this, for example, that's not simple or closed. That one, if I line those up, that's closed, but not simple. There's a quadrilateral, at least temporarily, so that's closed and simple. Okay, if I take, let's see what else I can do here. There's a simple plane curve, not polygonal. That one's well, it's not wanting to do what I want it to do here. So if we take something like this, that's not simple and it's not closed. If we take something like this, that one's simple and closed. Not simple and closed. So you have lots of different things there, okay? If we want to make a polygon in GeoGebra, then you want to make line segments. For example, that's a general quadrilateral. We can move this around. I say it's a general quadrilateral. It can be manipulated in such a way that it generates to a triangle or a line segment, or even, if I manipulate it to a point. It can also be manipulated in such a way that it's no longer simple, in which case it's not a quadrilateral. But it does include all quadrilaterals, like that one and this one and that one. That's not a quadrilateral. Okay, if you use the polygon tool here, that not only makes, in this case, a pentagon, but it also makes the interior of the pentagon. So this is the interior of this closed plane figure, but that is not part of the pentagon itself, not part of the polygon. The exterior is out here. Notice that we can, there is a circle that we can draw that's going to include all of the interior. But no matter how big we draw it, there's not going to be any circle big enough to contain all of the exterior. Okay, so hopefully that helps explain a little bit about some of these different things. Now, then we could prove as a proposition that a triangle, or also known as a trigon, is a three-sided polygon. And then, once we've defined a polygon, which required that we define what was meant by all these other terms, we can define now a quadrilateral as a four-sided polygon. Another very, very not very often used term is a tetragon, is another name for a quadrilateral. But we'll normally use the term quadrilateral for a four-sided polygon. Okay, and if we take this as the definition, then this alternative definition up here, where is it? This one here, could be proved as a proposition. Or if we take this as a definition, and once we get all these other definitions here, we can prove this as a proposition. But either way, even though it was convenient to talk about a triangle without getting into the weeds of all these different things that could go wrong with polygons, it's useful at this point to go ahead and define in general what's meant by polygon, and then go ahead and use that to define a quadrilateral as a four-sided polygon. Along the way, it required us to talk about things like defining a plane curve, a polygonal curve, a simple plane curve, a simple curve, a closed curve, and so forth, and put those things together to get this. So we have this sort of hierarchy here. We have geometric figures, continuous curves, plane curves, simple plane curves here. That includes things like lines, rays, line segments. We have polygonal curves, okay, and we have closed curves. Closed and simple would be called closed, simple, and planar. All three is a closed plane figure. That includes circles. And if it's a closed plane figure and a polygonal curve, that's where polygons live. They are all these things above. They're polygonal curves, closed plane figures, plane curves, simple curves, closed curves, continuous curves, and geometric figures. Now, we studied a lot about triangles and classified them further as scalene or isosceles, and under isosceles we had equilateral triangles. And we classified them some other ways as well. But then we can talk about quadrilaterals, pentagons, and hexagons. So one of the most obvious things to do when classifying polygons is to classify them by the number of sides. A triangle or trigon has 3 sides. That's the least number of sides that we can have. Quadrilateral is 4. Pentagon is 5 sides. Hexagon 6 sides. Heptagon is 7, although I've heard septagon used as well. We will use heptagon. Octagon is 8 sides. Nonagon is 9 sides. Decagon is 10 sides. 12 is dodecagon. And in general, if it has n sides, we could call it an n-gon. Now, if some geometers relax their what would be our definitions to include what we call an angle in spherical geometry, the union of 2 rays, okay, with a common endpoint, is going to have a vertex of that angle, but those 2 rays are going to meet also at the antipodal point. That is a closed plane figure in spherical geometry, okay, and it is made up of line segments, so it's a closed, okay, but if we want to consider that a polygon, it would need to have, could only have 2 sides, okay, but they're not all. It's not really a polygonal curve in spherical geometry the way we defined it, because those are rays, not line segments for the sides. But some people would call that a digon, in that case, a 2-sided polygon. We will not consider those things polygons in which we do not consider its sides line segments. Okay, so in all 4 of the geometries we've talked about, unified geometry, that's spherical, hyperbolic, taxicab, and Euclidean geometry, polygons have at least 3 sides. Now, there are some naming conventions for polygons up to many sides. Here's a Wikipedia article. You can see the link there. I'm going to go to it. And here is a naming convention for polygons up to 100 million sides. Isn't that ridiculous? So using basically Greek numbering system, and you can put these things together. Here's the sides up to 9. A decagon is 10, and then hendecagon or undecagon. There's sometimes there are 2 different possibilities here for the name, and so you can just go through, and they're all different kinds of names here. We're not going to mess with that in my class. In my class, we're going to just basically learn these names for sides 3, 4, 5, 6, 7, 8, 9, 10, and 12. And any others, we're just going to call them an n-gon. For example, if it's got 43 sides, instead of naming it however it was named in that list of polygons, we're just going to name it a 43-gon, right? And if we don't know how many sides it is, it has a fixed number of sides, but we don't know how many, then we'll just call it an n-gon. And once again, here's our taxonomy of curves. And now we have adequately defined lots of new geometric figures, including polygons and quadrilaterals.